Welcome back. We are now going to start using some of the tools that we've been developing in previous lectures in order to attack several problems in combinatorial optimization. And we're going to start with the bipartite matching problem, which will give us also the opportunity to look at a particular property of matrices called total unimodularity, which we're going to do in subsequent lectures. So let's just jump right into the basic definition of the bipartite matching problem. The problem is as follows. So we're given a graph. And this graph has a natural division into vertices of two types. You can call it a left and a right, or a blue and a red. So I have my graph. I'll write it in this way, but I'll also denote this partition of the vertices into, of course, a disjoint union. I'll just call this V1 and V2. And as always, E is a subset of the vertices, and I suspect many of you have seen bipartite graphs before, but what this really means is that I only have edges that cross over. And there's many characterizations of bipartite graphs. One natural characterization, if it's not naturally specified in a left and right or V1 and V2, is simply if every cycle is an even cycle, then a graph is bipartite. And you can obtain a left and right partition just by starting anywhere and starting counting off cycles and labeling things as V1 or V2 depending on what the parity is on their path. So let me just write down this characterization. I'll write it as a theorem, though it's pretty simple. A graph G is bipartite if and only if any cycle has an even length. So, for example, if you have a graph that has a triangle, it certainly cannot be bipartite. So we're going to do something that we've used in previous lectures, namely defining the incidence vector, we're going to map the graph problem of finding a bipartite matching into one where we can write it as a linear program and talk about polytopes and so on. So something important that we've already used in previous lectures and we're going to be using throughout is this following mapping. In any selection problem, I can map this problem into a set of corners of the cube. And then if I look at the convex hull of those corners, that defines a polytope, and therefore I can find maximum weight, minimum weight, etc. types of things. So we talked about this with flows, with shortest path, and we're going to use it again here for matching. So for a subset of the edges, any subset S of the edges, I'm going to define the vector chi S, which I'll call the incidence vector of S, and this is going to be an element in 0, 1 to the cardinality of the number of edges. The notation is very simple. I've got a 0 or 1 corresponding to every edge. It'll be a 1 if that edge is selected, and a 0 if the edge is not selected. It's a very easy way to just map into selection problems. So again, just to make it explicit, chi SE is equal to 1 if E belongs to the chosen subset S and 0 otherwise. And I'm going to define the the matching polytope. I'll denote this as P match of the graph G to just be the convex hull of all of these vectors. So this is the convex hull of chi M such that M is a matching. I suspect many of you know what a matching is, but let me remind you, M is a matching. I should write this more clearly. M is a subset of the edges. And it's a matching if no two edges are incident on the same vertex. So I can write this in the context of these incidence vectors chi m, and I could write this as follows. If I have any vertex v, I can look at the collection of edges that are incident to it and write that as delta of v, is all edges that touch it. We've used this notation before. And therefore, what do I need? The sum over all edges in delta of v of chi, oops, I've switched my notation here with subscript and superscript. I apologize for that. That should be m. So chi m e, this sum, remember chi m e is going to be just either zeros or ones, whether that edge is selected or not, should be less than 1. So it could be 0. You could have an edge that has no, you could have a vertex that has no edges in it, but you can't have more than 1. Okay, so this is the main thing that I have defined. This, in fact, is a subset of the unit cube. So maybe I should just note that this is in fact a subset of 0, 1 to the e, not just r to the e. Let's write down its LP relaxation. So I'll write this as Q of actually let's write down the what we had on the previous page and just make a simple observation that this is really the convex hull of all vectors that have the form that satisfy the sum over e in delta v xe less than 1 subject to xe in 0 or 1 for every e. So all I basically did is just write out coordinate-wise what these incidence vectors chi m are and just said which ones are allowed. So just flipping back, you can see that basically this is the only requirement right here on chi, other than that all of its entries should be either 0 or 1. So so I've been being a little sloppy here. This p match is the convex hull of all of these vectors. So the LP relaxation then is quite natural. I'll denote it by Q of G. And I'm going to obtain it simply by relaxing these integrality constraints to be in the following way. So Q of G, I'm going to define this as all x in Re such that 0, so every xe is greater than or equal to 0, and also the sum of these is less than 1. So you can see this of course also implies that individually each xe is less than 1. So if it's easier to write that, we could add it there. But that part is implied by the sum. So we certainly have it's immediate to see that Q of G, just by virtue of the fact that it's a relaxation, is a superset of P match of G. Well, it turns out that if G is a bipartite graph, this relaxation is exact. if G is bipartite, then Q of G, in fact, is equal to P match of G. And at that point, we can find matchings by solving linear programs. We can investigate what duality does, etc. Leverage all the tools that we have so far. So let's have a look and quickly go through this theorem just so we can get into the spirit of things. So first of all, the first result we already stated, and it's basically immediate. So this containment is clear, and you can just check. But it basically comes from the fact that it is a relaxation. If you want it to be explicit, you could take any matching and just verify that it satisfies the constraints of Q, and of course it does. That's essentially the process we went through by writing out the integer version of it. So let's look at the reverse inclusion, because this is what's interesting. So now let's in the next 4 slides we're going to show the reverse inclusion. So to show that Q of G is contained in P match of G, we're going to take an arbitrary element of Q, and we'll see if it's contained in P match. So what do we need to do to write it like this? P match is not specified in terms of inequalities. Yes, there are some inequalities, but the only inequalities in P match are also already contained in Q, so that's not going to help us. So we don't have a list of inequalities to check. What we have to do to show that X is in P match is to write it as a convex combination of those chi vectors, because that's the only thing that we know is in P match. That is how our description of P is specified. And again, this is an important point to belabor, having talked about simplex and the ellipsoid algorithm. All of those work by having a system of inequalities that define the polytope. And without that, we can't run either one of those algorithms. So that's why, even though P match is a polytope, it's a polytope in low dimensions, we can't just say that since this is a polytope, I can minimize a linear function over that polytope. That's just linear programming. That's not correct. So linear programming is only becomes efficient when we have a particular convenient representation of the polytope. And in a way, that's kind of the story for this whole class. This is what we're trying to do. Okay, so let's do this. I'm going to let so X is a vector of between 0 and 1, and it has an element for each of its coordinates corresponds to an edge. So let F equal the support of X. In other words, F is a subset of the edges corresponding to, and E is in F exactly if and only if XE happens to be strictly greater than 0. Okay, so this is what this means. And our proof is now going to follow by induction on the size of F. So the proof is by induction on the cardinality of F, and the base case is immediate. If X is all zeros, of course, it is part of P match, and if it has one non-zero, it is in the convex hull of 2 matchings. Remember, we're not talking about perfect matchings here. Okay, so now we're going to use this. We're going to assume that this holds for F of any particular size and prove that it holds for one more. So what could F be? We've taken the problem back to a combinatorial problem. And this is going to be, again, one of the staples of the tools and the kind of thinking that we're going to use. X is a vector that has fractions, etc., but we're also going to now use the combinatorial structure implied by X to help us reason about what X is. So what could F be? F is a set of edges. So let's suppose that F contains a cycle. we're going to use this fact to reduce to our induction hypothesis. If f has a cycle, our graph is bipartite. This must be an odd cycle. So G is bipartite. Cycle must be even. And here's what we're going to do. Now let's let D be a vector that has zeros, plus ones, and minus ones for every edge. And it just has plus one and minus one alternating along the cycle. This is simple, but let me just draw a picture. So I guess I don't know why I made it so complicated. Let me make my life easier here. And so it would be plus one, minus one, plus one, minus one along those edges of the cycle. Now, again, it also has to be on the support of F. So the support of D is certainly a subset of F, which is equal to the support of X. That means that every coefficient of D that's not zero coincides with an element of X that is strictly positive. And so what does that mean? That means let's look at this sum of E and delta of V of X plus or minus some small epsilon D. Okay, you see what my notation here. So usually we had just XE, but I'm looking now at the vector X plus or minus epsilon times D, subscript E, the eth element of that, and I'm summing over those. Now, note that this is, of course, the sum, what I had before. This is the sum of E and delta of V of XE plus or minus epsilon times the sum of DE, E and delta of V. But because it's alternating, then this has to be equal to 0. Okay, so this is therefore less than or equal to 1. And what this tells me is that this is now feasible. So this is a feasible vector. Why is that? If epsilon is small enough, then we know that X plus or minus epsilon D is greater than or equal to 0, because D only has plus ones or minus ones where I have support, where XE is strictly positive. So as long as I take epsilon small enough, there are no issues. There are no issues here. Okay, so now I'm just going to take epsilon 1 and epsilon 2 as big as possible in either direction. And you can see how I'm going to use my induction hypothesis. We're going a little bit slowly here just to kind of get into the spirit, but this idea we're going to use again and again. We're building an induction hypothesis. I'm writing X as the convex hull of two other vectors that have support strictly less. But if they have support strictly less, then I can imply my inductive hypothesis, and I'm in business, because I know each of those vectors can be written as a convex hull of incidence vectors of matchings, and therefore X can be written as an incidence vector of a matching. So to write out those details, now I'll just take epsilon 1 and epsilon 2 as large as possible, such that x1, which is equal to x plus epsilon 1d, belongs to Q of G, and similarly x2 equal to x minus epsilon 2d belongs to Q of G. But what happened? Why did we stop growing epsilon 1 and epsilon 2? Well, we stopped because some x became 0. So basically the point here is that we have achieved this. The support of xi is less than f minus 1 for both of these. And therefore, the inductive hypothesis holds, and we're in business. Okay, so if f has a cycle, we know that the theorem holds. So what's left? X does not have a cycle. So what does it mean that it doesn't have a cycle? What could the possibilities be? So if x, I'm now not writing left and right, but just writing nodes like I guess I could write it left and right if it's easier. So if x does not have a cycle, it means that it contains some single edges maybe, and it possibly contains some paths, something like that. But we note that there are actually two possibilities here. It could either, so we know it has no cycle, so it's a collection of paths. Actually, it doesn't have to be paths. Right? It could be something like this is allowed. So it is a collection of trees. This is called a forest. So in this case, if f has no cycles, it means that f is a forest. This is a union of trees. But there are two ways, but a matching is also a forest. So I'm going to assume that it's a forest, but not a matching. And the only thing that differentiates, that makes it not a matching, is if it has a path of length at least 2. So not a match. So if it's not a matching, it means there exists some path, a path of maximal length, and that length is greater than or equal to 2. So I'm writing a couple things here. I'm saying let p tilde be a path of maximal length in f. And by the way, because f is not a matching, this path has length more than 2. So now let's look at the edges in P. And my claim is that if for any E in this path, P tilde, certainly we know that XE is positive because it's part of the support, so by definition. But now I'm also claiming that it is strictly less than 1. So I'll just leave this as an exercise. Why do we have to have XE less than 1 in this case? Okay, so now we're going to do the same story. So let me just draw out my P here. So perhaps this is P, and I'm going to define a vector D that has plus 1s, minus 1s, and 0s, and again just alternates plus 1, minus 1, plus 1, minus 1 on the path. So I'll just write same as in previous slide. Now I can no longer assert that because this may not be it may not be even. So I might have edges that are that are left alone like that. Right? So I can no longer assert that that the sum over D is going to necessarily cancel out as it did before. Nevertheless, as before, I claim that for epsilon small enough, x plus or minus epsilon d belongs to Q of G. And again, this is because xe is not only strictly positive, but also strictly less than 1. So now the rest of this case proceeds as before. So then we proceed as before and invoke the induction hypothesis. Namely, we choose epsilon 1, epsilon 2, x plus or minus epsilon 1d or minus epsilon 2d is going to have support strictly less, and so on. So our induction hypothesis applies. What is our last remaining case? Our last remaining case is that F is itself a matching. Right? So the support of X, to remind you, this is the support of X, is itself a matching. So now what do I need to show? I need to show that I can write X as a convex combination of matchings. Of matching incidence vectors. So I need to write X is equal to the sum of lambda I chi mi, where the lambda I are non-negative and sum to 1. So this is what I need to do. So let's order the vertices, or order the elements of X as follows. So order X so that X1 is less than X2, etc., is less than whatever its last element is. Okay, and now we just need to observe that X is equal to X1 times the incidence vector of a particular matching, which I'll define, F1, plus X2 minus X1 times the incidence vector of another, times the incidence vector of another matching, and so on, where this ith matching that I use is, so let me, actually, I made a mistake here. This really should be F, not E. So I've only ordered the elements of X that are non-zero. So those are the ones that I care about. We would just have a bunch of zeros otherwise, so it doesn't really change everything. But it makes this definition more convenient. So what is Fi? Fi is it's nodes I plus 1, etc., in the ordering that is implied by the coefficients of X. And I break ties in any arbitrary way if, say, xk is equal to xk plus 1. So that means that each Fi is a subset of F, and since F is a matching, then Fi is a matching. Implies that Fi is a matching. And that's basically all we need to check. So that means, so what we've done is we've shown that X is in Q of G implies that X is in P of G, and hence Q of G is equal to P of G, which is what we wanted to show. We're going to stop here and then pick it up again with more information about bipartite matchings in the next lecture.